So maybe I'll do a little faceless YouTube here today. I was speaking with a friend who said, I watched one of your videos and I was a little confused. And maybe, after several years of teaching, I've gotten better at doing this. We're going to talk about counting and specifically using different number systems. Um, it's easy to think about a number and think about how to convert it into another number, and that's usually a very common way of doing things. Like for example, if I have the number 10, that is a two-digit number. In general, we have the tens digit here and the one digit here, and it represents a number of items, 10 things. And if we naturally count those 10 things and we start at 1, then we go to 10, we actually do have 10 things. In the computer world, a lot of times we start counting at 0. And so in that case, if we start counting at 0, because 0 is a place that can be a unique identifier, 0 and 1, for instance. These can be uniquely represented, and so we have two things here. If I started in counting as 0, and I went to 1, 2, 3, 4, 5, 6, 7, 8, 9, and normally my next value would be 10. How many things would I have? I would have 11 things. 11, 11 objects here that could be represented by numbers. So in the computer world, what we do is we think about what types of objects can I represent by unique values. So naturally, when I naturally count things, I start at 1 and I count 1, 2, 3, 4, 5. And that's true. In this case, I have 11 things. I'm going to count them starting. This is the first thing. This is the second thing. This is the third thing. Fourth, fifth, sixth, seventh, eighth, ninth, 10th, and 11th thing. And so in a number system, a lot of times what I want to do is I don't want to use the second digit necessarily to represent a thing. I just want to use one digit to represent a thing. And so I use the hexadecimal numbering system, and I'm able to do something really cool. I'm able to use an extra 6 digits here to represent 16 things. And in this case, the decimal equivalent here would be all the same, all the way up to 9, and then it'd be with 10, 11, 12, 13, 14, and 15. But because we include 0, it is still 16 things. Okay? TH. Things. 16 things can be represented there. But we like to use the letters. And I will tell you why. Because in general, what I want to do is represent bytes. And so it is an interesting thing when we look at this hexadecimal value, this base 16, because what each one of these numbers can do is it can be represented by 4 bits. And so I get to do something pretty fun here. I'll represent this by 4 bits. Okay, and then we'll keep going. 8, 9, A, B, C, D, E, and F. This is always fun. Okay, so now if you see the pattern, you can see that I am actually just filling in the values from the right. From the left, sorry. And F gets to be all ones. And there is a numeric way that I can do this. So the next thing we talk about is place. Now, in the decimal world, we have a number, let's say 1,000. Okay. I have places. I have the ones place, the tens place, the hundreds place, and the thousands place. And so I can always break that out. If I have a number, I can, let's say I had a number of 1342. I would have 1,000 plus 300 plus 40 plus 2. Okay. Another way I could write this is 1,000 times 1 plus 300 times plus 100 times 3 plus 10 times 40 times 4, sorry, plus 1 times 2. That is equivalent. All right, we take the place and we multiply it by the value in that place to get the total, and we add it all together. In hexadecimal, or base 16, which is this number system with A through F, we do the same thing. This is actually what is in the ones place. So in the ones place right here on a decimal number, when I use base 10, that's what that is, base 10, I can go from 0 to 9. I can store 10 things there. Right? I can go from 0 to 9 in that spot. I can go from 0 to 9 in all of these spots. And when I use from 0 to 9, I'm storing up to 10 different items in that spot. And I can represent numbers that range from 0, 0, 0, 0, which I abbreviate as 0, all the way to 9999 before I have to add another place onto the left. In hexadecimal, base 16, this is hex, we call it hexadecimal, base 16. This is my ones place right here. And if I add another digit, I have a 16s place. So we're looking at place. We have the 16th place, and we have the ones place. So if I had a value that was 2, 3 in hex, and the way I represent a hex value is I put a 0x right there. That way I know that it's a hex value, and that's just convention. But what I'm saying is I'm saying take 2 or 16 times the 2 plus 3. This is my ones place, And this is my 16th place. And effectively what I have is 35. 32 plus 3, 35. This is my decimal equivalent of this number. Now, I can also do something else, right? I can do 0xc8. What is that? C is a value of 10 which is 16 times 10 plus 8. That's 168. All right? I can do any of these numbers. These values, C and 8, are represented by these binary values right here. There's always the same. If I put in two characters, C and then 8, let's do that. All right, we're going to just take C8 and we're going to put it in binary. And the way I'm figuring it out right now is I am just copying these values, C8 in binary. Now, here's what we get to do. A couple things. One, this is the 16th place, and this is the ones place. Now, I could do this a couple different ways. One, I could take whatever this number is. In this case, it's 10, 11, 12. And I can multiply it by 16. And I take the 8, right, which is 8, and multiply it by 1. All right. 12 times 16 is 160 plus 32. Sorry. 160 plus, 32. That's 192. Plus 8. Did I do that right? No, I didn't. I didn't do it right up here. C8, this should be 16 times 10. Oh, I did this wrong. It should be 12. 16 times 12 plus 8. If I would have done this, this would have been A8, right? That would have been proper. But I use C, so I got to do 12. 16 times 12 is 192 plus 8 is 200. Okay. Yeah, there we go. Okay, that's better. But so I have these two values. Now, I can do this a different way. And sometimes one's better than the other. I don't know. What I look at is also place. So what is the place of this? This is the ones place. This one is the twos place. This one is the fours and the eights. Okay, all right. So here, 4, 2, 1, 1, 2, 4, 8. What I'm doing each place is I'm doubling. In this case, what I'm doing with each place is I'm increasing by a factor of 16. Okay. In this case, I'm increasing by a factor of 2. I'm doubling. So right here, this particular one is the 16th place. This particular one is the 32nd place. This one is the 64th place, and this one is the 128th place. This never changes. Okay, so here's what I get to do if I want to do it this way. is I get to add 128 plus 64 plus 8. 128 plus 64 plus 8 is 200. Okay. Right. So I get to add these values up. I think in most cases, if I'm converting from hexadecimal to binary, it is much, much easier for me to just look at, have this chart memorized, and I'm just going to think, okay, a C is 12. So this is my 8 and this is my 4, right? So 8 plus 4 is 12, right? I can do it in 4-bit pieces much faster than I can do it in 8-bit pieces. Either way works. Whatever works for you, right? I just think that it's easier to think about it in terms of 16 pieces, and I can easily count. Right? I easily can tell an odd number from an even number because this value right here changes. 0, 1, 0, 1, 0, 1. All the odd numbers end in 1. All the even numbers end in 0. I can easily think about this from 8 and 8 and 4 is 12, right? Or 8 and 2 is 10. I can add these up really easy, right? So this makes converting a number like this really straightforward. What we see is when we look at a document. Let me show you a document in a hex editor, and you can see what that looks like. So I like using the browser-based hex editor because it lets us we can see what we're doing. So this is the hex editor where I can load up a file, and I'm going to just open up a little, I don't know, it doesn't matter. Let's see, maybe a little image that I can load up, and let's see. Who knows? Who cares, right? Let's see. Something. There we go. Some little 2 kilobyte file. We don't know what's in there. Okay, so. All right. And so what you can see is that in each location that is 1 byte, there has been 2 values that have been populated. And so I could easily convert this file to binary because all I would have to do is convert a 4, 1, 0, 0, 0, and a 3, 0, 1, 0, 1, right? And I could easily make that into a 1 byte value. And so if I'm creating, if I'm thinking about transitioning this into a binary file, doing the little 4-bit values is pretty straightforward. And so one of the first questions that someone would ask when they see data loaded up in this format is, what is this over here? And what this is a code table, an ASCII, American Standard Code for Information Interchange code table. We can search for that. You can find it online, ASCII code table. And you have a value for every hexadecimal character. And so we can look at one right here. This is the value for each character that could appear. And so, as you can see, they're all listed here, 1D, 1E, 1F, and it keeps going to 2A, 2C, 2E, 2F, and we get into the numbers here, right? These are the values that will be used to convert some hexadecimal value with an actual ASCII value that's a printable, and the idea is it's a printable character. So I can find something maybe that looks easy. It's like a 3. That's 4 alpha. right? That 3. Oh no, okay, that's a 7. Let's see. That's number 37. Okay, and we'll go look and we'll see 37. Yeah, there's a 7 right there. Um, so this is the American Standard Code for Information Interchange, ASCII character set um, values. Now, Unicode is another character set table that we use, and Unicode is a modern. It has support for not just 1 byte, but it has support for 2 bytes for each um, address in the table. And so, in that particular case, there are a exorbitant amount of things that can be stored in that table. And so, this is actually a byte-centric file where the bytes are arrayed, and starting with the first byte value here, and going down all the way to the last byte value that's on the disk. And so one thing that you might see, and you would use this often if you're looking at like network traffic, for instance, is that this particular um, this particular row we know holds 16 items. So we have offset 0 and offset 15 right here, or offset hexadecimal 15 right here, and then it starts over at 1. So this is the traditional way that the file is depicted with the 16 bytes in a row. So and you can even see the line right here that goes down the middle. That is a byte separator. There's 8 bytes on one side and 8 bytes on the other side of the separator. So I can immediately point out, for example, to Bravo, and I'm going to be right there at 2 Bravo, right? That is 1 2 Bravo. That is the offset, and I can read that byte value right there in that location, and I can see what that is, and immediately be able to convert it if I had the right table. There's our value. Now the thing about the characters here is that many of these characters are unprintable characters, and so that's why you get maybe some garbage looking stuff right here. Is you get these unprintable characters. They don't really correspond with a letter of the alphabet or language. They correspond with maybe a control code or some type of building block code. These little shapes are in there also. Let me see if we can find the shapes. They should be in here somewhere. There are characters that are line building or screen building characters, and I don't really see them in here. But they could help us build menus and build different types of squares and blocks. And so, in a text-based terminal, these little characters were used at one time to create the panels and menu borders and things like that. And so they're still in the table even today. So this is called a hex editor, and every program that sniffs network traffic is going to use a hex table, and I will show you an example with the Wireshark program. Wireshark actually sniffs the traffic on the interface, and so we'll go look at our traffic PCAP file. This is a fun little file, and it has just a little bit of sniff traffic in there. And as you can see, here is one packet on the wire, and then here is our little table with our 8 bytes over here and 8 bytes over here. And it makes it really easy for us to look and see exactly what byte we're looking for in the file. And so I can copy this data, I can paste it, But Wireshark really analyzes the traffic for me and helps me understand what is inside the data packet and what components are part of the transmission and what parts might be calculated from that transmission. But when we count in a numbering system, it's all designed to be done for a purpose. So I'm not just making this up. I'm actually lining this up with byte values in my memory, and I'm using bits. These 4-bit values here, 2 of those work out to be 8 bits. 8 bits works out to be 1 byte. And then I use the hexadecimal because it's an easy way to represent the 4 bits. I can represent it with 1 character. So that is why we use that base 16. One of the things that I like to tell my students, the trivia fact, is that in the old days of sea trading, shipping, there was a number system based on dozens, and it was base 12. And so in the cargo world, you had 0 through 9 and E and T for 11 and 12. And so everything was based on 12. And that's where you come up with 12 times 12 is 144. It was cubic. It was a square number, and it was a way to stack cargo, and everything was done with base 12. So you would have dozens and grosses and even more number categories that would be squares of 12. It helped you calculate the amount of area on the ship that you could store cargo. And so base 10 is not really that effective of a number. It's used for counting. We have 10 fingers and 10 toes. But for other things, it's sometimes better to use different number systems. So I hope you enjoyed a little bit of counting in different number systems and how we did that. And if I have some other videos, hope you'll enjoy those on IP addressing and network subnetting. So thank you.